It is great to be back. I hope you had a great summer and everything worked fine for you. Today, we are going to start our series of the MPP seminar with a talk by Professor Panza. And
kindly, Professor, please.
Yes, yes. And he's going to tell us about how Frege's definitions of real numbers are actually consistent, which is still to see. Okay, please.
Thank you very much. So, this is for the MPP students. There is an important news in the room here. There are 5 screens. So, if you do not understand the screen, you can try to understand. So, you have 5 screens which you can try to understand.
There's no excuses.
No excuses. No excuses. In one of the screens, you should understand. Okay. I make a premise. There will be a medium part of my talk that will be quite boring and possibly difficult comprehensible. But I explain to you why and why I cannot eliminate it. I cannot eliminate it. I can go quickly, but I cannot eliminate because the basic idea is that in this medium part of my talk, I will present you some formulas. And the basic argument that I present is that this formula can be written. So if this formula would not be able to be written, my argument would break down. So I will show you the formulas. I think that nobody of you, even the best logician, can very quickly understand all the formula. What is important is not what is written. Then if you want to, we come back to some formula to look in detail. But what is important is that I can write this formula in the language that I have. Okay, this is what is relevant. I can write. Of course, if you do not look at the formula in detail, you can doubt that I can write it, because you can imagine that it can be written. I ask you to trust me. And we have some doubt, we will come back to some of them and during the discussion. Okay? Okay. Okay. John and Giselle, welcome. John and Giselle, do you agree with my daughter and my son?
We communicated with.
Perfect. You want my telephone?
No, it's okay.
Okay. Sorry, family question, but fundamental. 40 years ago, Christian Wright suggested a way to vindicate Frege's definition of natural numbers and disprove of Peano's second-order axioms. All that is important to notice about this important achievement is today what follows. One of the major ingredients of Frege's definition, responsible for the contradiction, basic law 5, which in a modern predicate setting is usually rendered as follows: the extension of X is identical to the extension of Y if and only if X and Y are coextensional, is eliminated. In Wright's new definition, this law is simply omitted. In the absence of it, natural number can no longer be identified with appropriate extensions of concept as originally suggested by Frege. So the basic idea of Christian Wright is to eliminate basic law 5. Without basic law 5, the contradiction disappears. To replace basic law 5 with a principle that is probably consistent, and to show that using this principle instead of basic law 5, we can define natural number and prove all the basic theorem about it. What is significant is the new principle that Christian Wright decided to put in the place of basic law 5 is also present in Frege as a theorem that derives from basic law 5. And what is relevant is that all the proof of Frege does not depend on basic law 5, but on this theorem proved by basic law 5. This is why Article 5 can be eliminated, because what is relevant is this theorem. Of course, there is a long discussion whether it is legitimate to use this theorem as an axiom. That is your principle, but this is long discussion that I cannot consider today. And also what is important to notice is that basic law 5 is not the only reason for the contradiction of Frege system. Okay? It's only in presence of full comprehension that basic law 5 is contradictory. And this is the reason in which my reconstruction of Frege definition of reals, I will conserve basic law 5 as it is. This is possible because a consistent principle, which proves based on basic law 5, still allowing to implicitly define a special sort of object associated with concept, is taken as an axiom. This is HP, Young principle. The number of x is identical to the number of y if and only if x and y are equinumerical. What is equinumerous? So what is relevant is that what is written there, x equinumerous to y, is a formula that I can write in second order logic. So this is sentence of second order logic. In fact, this is not the formula, this is an abbreviation of a long formula.
So this is the theorem that the right
Yes.
wants to substitute.
No, this is the theorem that Frege proved.
Right.
The right take as
The
a
right says we use this
we can
instead
use
of
this
the
exactly. And this is a formula, long formula that says essentially there is a rejection between the object defined under x and the object defined under y.
You said that this is consistent.
Sorry?
You said that this is consistent.
This is proved to be equiconsistent with Peano second order arithmetic. The proof of equiconsistency has been given by Grundgesetze 1 year after the publication of the book. Of course, we cannot prove that it's in absolute consistent. Well, it does not make more sense to say what does it mean to be absolute consistent. The proof it is equiconsistent with Peano second order arithmetic and then with set theory. Okay, this principle also allows to identify some of these objects that probably have the same structural properties the Frege's definition assigned to the extension is identified with natural numbers. The proof of this fact essentially goes as Frege original one, thought in a modifying logical setting. The modification consists in replacing the Frege formal system based on the object function duality with a predicate system, second order logic, where Frege terms are replaced by formulas and function by predicate. This modification allows adopting a relevant simplification, both in Frege's definition and his proof, but is not essential for the successfulness of the vindication enterprise. Since Frege more general original setting might be reproduced within the new predicate setting, if some appropriate assumption or Frege spirit are made, and the new consistent definition might also be restated within the original setting. This is why I adopt the same modification at least in right and tacitly project Frege's definition within the predicate setting provided by second order logic. So what I will give you is not exactly Frege definition, it's the projection of Frege definition of second order logic. But it is, translation is innocent enough, I suppose. If you disagree, we will discuss it. But practically the totality of this modern discussion about Frege, take it for granted. Adopting this modification is however not enough for making the same strategy, right, suggested from Frege's definition of natural numbers, also apply to his envisaged definition of real numbers. The reason why I say envisaged definition are this. Frege's definition was never completed, Frege's definition of real numbers. And for theory, the proof was not provided that the real number form an appropriate complete field. This definition should have taken place in the second and third volume of the Grundgesetze, the big, great book of Frege, and based on the same subjacent formal system as the definition of natural numbers. The second volume appeared in 1903, but contains only part of the definition. A few weeks before its publication, when in fact the typographer already composed a large part of the book, Frege received Russell letter informing him of the well-known paradox. This paradox affects the whole system, and despite his final tentative to solve it, convinced Frege to abandon this project, and it is the reason which the third volume never appeared. I will show today that Frege was wrong in abandoning this project. The second volume contains, however, a crucial part of the definition and a broad description of the way it should have been completed. It is enough to make it clear that Frege's strategy cannot apply to the case of real numbers. To see it, some further remarks are necessary. Frege's proposal was defining real numbers as ratios of magnitudes. It did not properly suggest however to define magnitudes, and even less to identify them with appropriate particular objects or relations. He rather provided, in a second volume, a structural definition of domains of magnitudes. For a mathematician, essentially, a domain of magnitude is mutatis mutandis, a additive and totally ordered and complete group of permutations. Okay? He rather provided, in a second volume, a structural definition of domain of magnitudes. Its aim was fixing the structure that the objects falling under a first-level concept are to instantiate for the extension of this concept to be such a domain. Again, the definition is structural, but not purely so, as it were, since it required that under a concept was extension is domain of magnitudes, only for extension of first-level binary relation working as permutation on a suggested domain of objects. What I mean is that this is a group, but it's not a group where elements are whatever. The group of elements are extension of binary relation. This request cannot be avoided. Since the structure is additive, and this definition requires additive inverse at an additive identity. And for the definition to be general enough in what logic, is that to be avoided to implicitly define the relevant addition and identity while defining the structure itself. It cannot say, let a domain of magnitude be a set of objects with an addition. I need to say which addition and to define it logically. Otherwise, I do algebra, not logic. Addition and identity are explicitly provided by the very logical nature of binary and functional relation, namely by their compositionality, addition, and identity relation, at zero.
I don't understand where the permutations come into the picture. In my mind, when you talk about the, what do you call it, this domain of magnitudes, could segments be the domain of magnitude?
No, this is a very interesting question. For Frege, segments are not magnitudes, lengths are magnitudes. And what is a length? A length is a binary relation between a certain unity as another.
Okay.
So this is the relation on which it.
But where do the permutations come?
Sorry?
Where do the permutations come?
The permutation came by a definition, by a quote that he gave of Gauss. And the idea is basically, first of all, it worked very well logically speaking. If you take permutation, you have a lot of facilities in the definition. But essentially, the idea is that you can permute because you can change the unit. What is relevant is not what the unit that you take, but when you change the unit of measures, you will have another measure, and what's relevant is what you do with it. Okay? This is what it does. So magnitude for him, the element of a domain of magnitude are extensions of permutations. To be more precise, are extension of binary relations that are functional, injective, and subjective on the domain of subject objects.
I don't want to interrupt the flow because I don't want to bother people, but later on you have to explain again to me this permutation thing. I'm not totally.
Sorry?
I don't understand this permutation thing. I mean, if the domain are binary because it's pair of segments, so you have a segment you consider the unit and another, and so then now you have this domain and the ratio is what I guess is considered to be the real number. I don't understand what is permuting. What is permuting? But we can talk later. We don't have to address it now.
Okay.
Marco, could I ask? So why doesn't he just do something like, take any putative domain of magnitudes implicitly define what a domain of magnitudes is by giving like group theoretic axioms or something like that. And
Because
that's
this would not be logical.
that's
for
not
people.
logical. Okay.
That would not be logical.
Even if you
This-
have like a
this- the
categoristic-
very problem that Frege had is they want to control what they're speaking about. And when you say let a group to be a set, what is a set? And it is an addition. What is the addition?
Okay.
Oh, I don't mean that Frege was right in urging this attitude, but this was his point.
Yeah.
I cannot speak of what I do not know what it is.
Is this related to the like Caesar objection and
If
Grundgesetze?
you want, yes, if you want. Okay. The reason Frege strategy cannot apply in this case are these. The definition of the domain of magnitude indispensably requires that the element of a domain of magnitude to be intimately related to first level binary relation, just the definition of natural number requires that this number be intimately related to first level concept. So both of them are extensions. But it also requires that the intimate connection linking this element to this relation be the same as that which make it possible to associate to a first level concept a domain of object identified in terms of condition to be met by the very object falling under this concept, so as to make this domain count as a domain of magnitude. I explain myself. Magnitude are the extension of binary relation, and the domain of magnitude is an extension of a concept. So extension enter here in two different roles. Okay, they are the element of the domain, and the domain is an extension. Okay, so you need a notion that does the two jobs, and you need the same notion able to do the two jobs, because otherwise you need the two different principles. And of course, you cannot do the two jobs with your principle. Your principle can make one job, not the other. Okay? It seems clear this double task can be achieved neither by your principle nor by any other principle specifically proper to real number. A Young principle is proper to natural ones. So you need enough neutral principles to make this double job. But there is more. This intimate connection is also required to be neutral enough, as it were, to make the element of a domain of magnitude be supposed to have no other particular features than those depending on their meeting the relative additive structure. So I cannot say their length. In particular, it has to avoid any possibility of identifying any particular such element other than the additive identity, since any such identification would involve an admissible loss of generality. So we do not know, we do not define individually magnitude. The only magnitude that we define individually is the zero. That is the extension of identity relation. Okay, this is very fundamental for the end domain talk. Once the domain of magnitude are defined, ratio of them are also be shown, which inevitably requires a fourth principle, different in nature from that which provides this intimate connection, so that the final definition requires at least two appropriate principles, other than the action of logic. So, bicycle 5, and something else that is useful to define ratio on domain of magnitude.
Why is those ratios needed?
So,
Why do we need ratios?
this is a very nice question.
You already have.
Frege defined real number 3 times.
Yeah.
It triple, because he thinks the real number are essentially ratios. And so he does not want to confound real number with magnitudes, because magnitudes form a group, real number form a ring or a field. Or magnitude does not make any sense to define.
So you can only add magnitudes, but if you want to
Exactly.
multiply them,
Number, we have to
you have to.
add ratios.
Okay.
So this is a basic idea. Of course, structurally speaking, when you define real numbers on a domain of magnitudes, you duplicate the structure of additive complete group, but with a multiplication that before there is not there. Additively speaking, you define real number 3 times. The third time I don't explain why. It's not so relevant for me. But that you define real number 3 times. So you say horrible. In a sense, it is horrible. But my point is not that it's horrible or not. My point is that we can do it consistently. If one wants to be faithful to the letter spirit of Frege's definition, It is to this further principle and only to it the one has to ask to provide the appropriate means for. Passing from the pure additive structure of domain of magnitude to a new structure involving two distinct operations, additive and multiplicative one, and then to distinct identity and additive and multiplicative one, to the second principle. Basic on both of these identities to define an appropriate metric, making ratios able to provide genuine measures of magnitudes. Observing this is already enough to make clear that, differently from that allowing to define domain of magnitude, the third principle for ratio is to be specific enough and then presumably mathematical rather than purely logical or analytic in nature. This makes clear why Friesland right operation strategy cannot be applied in this case. All the previous considerations only concern the very logical form of Frege's definition and the possible vindication of it. For the purely philosophical consideration of this sort and other similar sorts, I certainly provide other reasons to suggest that the Frege's right strategy for natural number cannot apply to real number. I leave them apart here because I want to make my point as neutral as possible with respect to further philosophical evaluation, to allow philosophical concern to be based on it, rather than providing a base for it. Having a right strategy for natural number cannot apply to real number is, of course, not my main point today. What is more relevant is asking whether an alternative and successful strategy is available to vindicate Frege's definition of and approach to real numbers. At the best of my knowledge, for a deeply different alternative and been suggested until today, is not vindicate his approach, at least to reconstruct his definition or some variant of it in a consistent setting, or at least to get a consistent definition of real number within a Fregean framework. The first come back to Hilbert and Bernays' Grundlagen der Mathematik, in particular to paragraph C of the supplement 4 of the second volume, appeared in 34. This idea here is to define a real number within second-order arithmetic by mimic Frege's sketch of a possible existence proof of non-empty domain of magnitudes. To Hilbert and Bernays do nothing to suggest any connection between the idea and Frege legacy. It is enough to look at this definition to see how it can be adapted to make this number directly defined as the element of an arithmetic instance of Frege additive structure on which an appropriate multiplication can be defined. To using Fregean tools, this alternative is deeply non-Fregean in nature, since it ipso facto makes real number arithmetical objects rather than mean for measuring magnitudes. So perhaps here explanation is important. Very, very, very mutatis mutandis, Hilbert's definition consists in taking a real number to be a pair composed by a natural number and the property of natural number. The natural number tell the integer part of the decimal notation, for example, 3. And then this is a sequence of 0, 1, according to whether this property is not appropriate by a number. So if this property is enjoyed by 1, the first one will be 1. If it is not enjoyed by 2, the second one will be 0, etc., etc. So we'll have here a succession of 0, and so this would be a way to represent it. And so we have real number as decimal expansions. Okay, these are the basic idea. Of course, this cannot be Frege. The idea is Frege, because this idea is Frege, because from Frege was to define that exists at least on the domain of magnitude, construct a model. This is the model constructed by Frege. But for Frege, it is a model that cannot be real number, because real numbers are essentially distinct from natural ones, because they're ratios, they are not arithmetical objects. So the idea came from Frege, but it's not Frege in nature. The same is true for the alternative suggested by Shapiro in his Frege Methodedeking, through the reference to Frege is this time explicit. The idea here is to start from Frege's arithmetic, that is the consistent version of the Frege definition of natural number, got in agreement to write strategy, and to add to it 3 new abstraction principles, that is axiom of this form. The abstract of alpha is identical to the abstract of beta, if and only if there is equivalent relation to alpha and beta. So conceived to define relative number as the abstract of the first principle directly applied to natural numbers, real numbers, pairs of natural numbers. Clear what it means. So the identity relation is a tier of Dawkins relation, plus 1, A plus C equal B plus D. Rational number is the abstract of the second principle applied to relative numbers. So we take the natural, we have the relative. Then we take the relative, we have the rational, and relative number as the and the real numbers are the abstract of the first principle applied to appropriate properties of rational number this time, of course, because it will change the cardinality.
What is the third principle?
The third principle is essentially a way to write the Dedekind in the Carter in the language of abstraction, essentially speaking.
When you say that there's an equivalence relation between alpha and beta, what do you mean? Or there's a bijective relation, or?
To be more precise, it's not an equivalence relation between alpha and beta, because if alpha and beta can be object, so we have an equivalence relation. But if alpha and beta predicate, you have to be in third order logic to have an equivalence relation. So what you have, to be more precise, is a formula that is transitive. It's an equivalent formula. Okay.
An equivalence relation is a set of pairs, right? Or a formula,
For example,
but of elements of the same thing. So what does it mean that there's an equivalent relation between the object alpha and the object beta?
No. So in this case, take the case of rational number, or relative number, that is the simplest one. You have the real one, and then you have the abstract of, so how does it work? It is one, let me remember, how does it work? I written it a long time. Yes, the abstract of the pair PQ is equal to the abstract, the abstract of the pair P and Q is equal to the abstract of the pair S if and only if P plus R equal Q plus S. Okay? And this is a formula that has the property of an equivalence relation. Okay? And the alpha and the beta are pairs in this case. Okay?
So it's...
It results in a definition of real number as Dedekind cuts obtained with Frege tools used for pursuing a depthly non-Frege perspective. Because again, real numbers are defined as arithmetical objects, what Frege absolutely not want. A closer perspective, Frege 1 is that pursued by definition, suggested by our late friend Bob Hale in Real by Abstraction, somehow anticipated in a type of writing written by Donna Scott, presenting his 1958 lecture to the University of Chicago. The idea here is to provide an algebraic and quasi-theoretical definition of the structure of positive domain of magnitude as complete semigroup. So this is exactly make algebra, as you say. Then to appeal to a first-order abstraction principle, moving to the Euclid definition of proportionality to define a positive real number as ratio on whatever instance of such structures. In such a way, to make any single such ratio identifiable as the ratio of a pair of elements of any possible such instance. What that means, we have an infinity of domain of magnitudes, but the ratio of one domain of magnitude is the identical object to the ratio of another domain of magnitude. So there is a lot of domain of magnitude, but only one domain of real numbers. Okay? Took this idea as well as that of appealing to an appropriate version of Euclid definition of proportionality to implement it genuinely Frege, both in nature and in spirit, providing an algebraic and quasi-theoretical definition of the structure of positive domain of magnitude is as far as possible from Frege's approach that was both radically anti-algebraic and anti-theoretical. The fourth alternative has been suggested by Francisco Bocconi and myself in a recent paper appeared on the Review of Symbolic Logic. The idea here is to follow step by step Frege's definition of domain of magnitude and the sketch for the definition of the real number and ratio on them, by avoiding the contradiction by simply eliminating extensions and replacing them with inner relation and concept of the appropriate level. Structurally speaking, this provides a definition very close to Frege's original one, with the crucial difference, however, of making neither magnitude nor their domain genuine objects, requiring a third-order logic, appealing to a third-order version of Euclid's definition of proportionality as a downward abstraction principle, etc. This is not so important. To my mind, this is closer to Frege's original, but still quite far off it, because instead of magnitude, are no more objects, are relations. So, and I need the third-order logic. My purpose today is to advance a fifth alternative, one that does not only vindicate Frege's definition and approach, but strictly reproduce them as are, took in a consistent setting. Getting this setting is not a matter of replacing some Frege tools with others, nor of adding some new ones. It's just a matter of subtracting one tool pervasively used by Frege, but also responsible together with basic law for the contradiction by so avoiding inconsistency. And observing them when things are looked at in detail, this tool is indispensable to the successfulness of the definition. So the point is not to add something, it's simply to eliminate something. And to show that something that they eliminate is indispensable. Provided that some of Frege's definition and the corresponding value are replaced not with predicate and atomic closed formula, as usually, but rather with non-atomic open formulas. I will explain in which way. This is why I say that in my title, the Frege definition as such is consistent. Not that this is so for some appropriate rephrasing of it, nor that this definition is amendable as to make it consistent. If I'm right, the definition which I will shortly present here is just Frege's original definition of domain and magnitude, followed by that which should presumably have been the subsequent definition of real numbers that he was planning to provide, with only a final slight difference, which might however be avoided with a little bit of supplementary work, which is in fact mathematically useless. I will avoid to add a further stage to the definition of ratio of domain and magnitude, only useful to make a real number form in turn an instance of the structure of domain and magnitude. This is the reason which I give three definitions: magnitude, ratio, and I say no, real number are not ratio, because the real number has to be magnitude in itself. So I needed to make a third definition that shows the real number domain and magnitude. This is completely crazy. So I forget that this part. But in fact, it's crazy, but technically possible to do. The tool which I suggest to subtract from Frege's setting is the unrestricted rule of replacement of Roman function letter with Roman function makers, and vice versa, within the predicate setting is translated in an action scheme of full compression. So in modern terms, I eliminate full compression. To be more precise, I suggest to limit this rule by making it transformed in nothing but predicative compression, namely the two-fiction schema, where phi and psi are formula with second-order quantifiers, and this means that I can use parameters. Okay, so the formula phi and psi can contain open variable other than x in x and y, under the condition that the quantifier on this open variable here. Okay, so I can use a schema of comprehension with parameter, not to define one predicate, but a family of predicate that depends on the value of the parameter. Okay, this is very, very common, very familiar, very usual, and also Frege in some sense, even mutatis mutandis, use this tool. As it is very well known, this makes basic law harmless, and it follows it to continue the definition and allows it to continue to define extension of a first level concept, so limiting the range of concepts that are probably supposed to exist. So what is important is that comprehension gives a sufficient reason for the existence, a sufficient condition for the existence of predicate, not a necessary one. So if I predicative, the only thing that I that I impose its existence of predicative concept. For the other concept, they can exist or not exist. It depends. Insofar as Russell concept provides a contradiction, the proof of the contradiction simply proves that the concept does not exist. Finished. What is essentially the idea that is behind the theory and action of comprehension theory? Okay, observing this is certainly not scoop. The fact that the particle of I with predicative comprehension is consistent is very well known, at least from 50 years. Well, it seems to me that the first one that proved it is Lindenburg. I am not sure, possibly someone else. Lindenburg, in his PhD student, I can be wrong. Well, it is observed, it is originally also observed that the theory that is got this way is too weak for the purpose of satisfactorily defining natural number, or better, to prove the existence of the successor. So the fact that I can make the system of Frege consistent by limiting comprehension to predicative comprehension is very well known. The point is that this is not enough to define natural number. Why? Because with predicative comprehension, I cannot prove the existence of the successor. So I cannot prove the natural number is infinite. For short, call this theory FD predicative comprehension, for Frege-Diatic second order theory with predicate comprehension. It is provided by the system of logical L2DPC of Diatic Sol with predicative comprehension plus a restrictive basic of I and the extension of predicative comprehension to formulas involving the functional constant implicitly defined in basic of I. So what does it mean? I take logic with predicative comprehension. I add basic of 5, so now I have new terms, a new element, and so now I extend the comprehension to formula that contain this operator. Okay? It might appear natural to think that from the fact that this theory is too weak for providing a satisfactory definition of natural numbers, it follows that it is a fortiori too weak for providing a satisfactory definition of domain of magnitude, and offering an appropriate base for the definition of real numbers and writing on them, because the structure of the domain of magnitude that is of a group, complete groups, additive groups, seem to be too strong, much more strong than the structure of omega sequence. So if I am not able to use this to do it, to define the omega sequence structure with this tool, how can I be able to define the structure of complete group? This is not so. This is what I will show. Okay, this is the second part of my talk, essentially. The crucial tool Frege uses in this definition, both natural and real number, is this function got by composition of the from function and the horizontal function. For the mathematician, C and C is what we today we call x and y. But Frege does not want to write x and y because he thinks that they are not variable, but placeholder. They simply indicate that there is a place free for putting some values. So you think the notion of variable is a bad notion because it does not understand what can be a quantity that's not fixed. Okay? So a function for him is not a value, is not an operator of a variable, is something with an empty space. It's a matrix that I can fail. And so he writes C and Z in order to make clear that it's not x and y. It's x, they are placeholder and not variable. Not so important for my topic today, but to make clear why I use this notation. By simplifying them a little bit, Frege's definition of this function, we can define this function like this one. This is equal to T. T and F are objects for Frege, the true and the false. This is the false. If exists a function x such that some function such that x is the extension of f, and fy is the true, that is a concept, because what is a concept for Frege is a function with values and the true and the false. And f, if does not exist, etc., etc. If we strap a function to values, that is, we transform this strange expression in a predicate expression in good logic of today, we have this definition, x and y if and only if it is true. So now it is not a function, it is a formula, okay? X from X is true if and only if exists a concept X, such X is the extension of this concept, and Y fall under this concept. Okay, this translates in our usual language today, what Frege has written in a functional language, which would make Y from X an open formula and horizontal function, useless. See, there is no more this strange function here that is exactly used to transform any object into value. But in the new setting, this can be eliminated and we can write things this way. This is purely hypothetical, already. Why it is hypothetical? Because look, I have second order quantification here. So I cannot define this relation in my system because I have no second order comprehension. I am not impredicative comprehension. So I cannot do it. If I did it, I would have contradiction. Okay? Unless I just accept this particular instance of comprehension, impredicative comprehension, and not predicative comprehension itself. So this cannot do that because I have not guaranteed that this relation exists. Because I have no impredicative comprehension. Okay? So I cannot do it. This is purely hypothetical, however, since the theory with full comprehension is probably inconsistent. But it is not worthless, since something similar can also be done within predicative comprehension. Nothing forbids, instead, to adopt the following abbreviation clause. It is exactly the same, but now it is not a relation, it's a formula. So when I write here, it's simply an abbreviation for this formula. And I simply introduce that for short. And it is not a predicate. So I don't need comprehension to that. It's simply a linguistic convention. Of course, the consequence of that is that I have nothing as the extension of this formula, because the extension are defined on predicate, not on formulas. So I can do it if and only if I do not need to have the extension of this relation. If I needed the extension of this relation, I could not do what I do, because I would need a predicate. But the predicate I cannot do, because it would be inconsistent. So all my point is simply that I do not need the extension of any predicate that Frege introduced by impredictive comprehension. The only extension that I need are extension of predicate that Frege introduced with predicative comprehension. So I do not need impredicative comprehension because I can replace any predicate that Frege introduced by predicative comprehension with open formulas. Okay? Okay. But rather to characterize these classes as extension of concepts which satisfy appropriate open formula. Now, what are domain of magnitudes? Domain of magnitude are simply no more the extension of a certain concept, because this would be contradictory. Domain of magnitude are formed by the object that satisfy under a certain formula rather than fall under a certain concept. Insofar as of this formula, I don't need to make extension. This I can do. For this purpose, we only need the following explicit definition, only censored by predicative comprehension. This is the notion of composition of a relation, and this is the inverse. Oh. So now this is predicative, so I have no problem. And in fact, I also do that. This is really not necessary. I could avoid it, but this is shortened. And this is the extension of the identity that is the zero of the additive system. But these two I could eliminate. I make it by short. With a little bit of work I can do. With this explicit definition, hence, we can write a number of appropriate open formula to associate to them a suitable abbreviation. Here, the most basic is one formula that tells that Z is the extension of the binary relation composed by the binary relation with extension X and Y. This one that says that Y is the extension of the inverse of the relative was extension of the relation was extension X. This say that X, plus y fall under the concept of x. We say that x, the inverse of x, fall under the concept of x. This is the extension of a binary functional relation, etc., etc. And this is to say that y is the domain of x. So this is a crucial point. What is the domain? Both to say that y is the domain of x, it means that both x and y are extension of concept. Under that was extension is x, only file extension of binary relation. Under that was extension of y, file the extension, falling under that was extension of x, plus the extension, the inverse of the relation was extension file under this last concept, and the extension of the identity relation. To say very clear, the positive are the demigroup, and then to have the group, I add the inverse plus the zero. The domain, what is? The domain is the group that originates by the demigroup. Okay, I define the demigroup and I take its domain. And the demigroup is what you call a positive class. And then the domain of magnitude is the domain associated to a positive class. It is the group that extends the demigroup of the positive. In intuitive terms, the domain of a class of extension of binary relation is the class including this extension, together with the extension of the inverse relation and the extension of the identity relation. Then other formulas, I do not enter in detail, but these are all formulas that I will use to write my formulas. We are not able to write an open formula which is such that the objects that satisfy it are in Frege language positival classes. Intuitively speaking, this means that these objects, the positival classes themselves, are extension of concepts. Under this concept, only file extension of binary relations. These relations are all functional, and such that the inverse are also functional. More than that, they are all permutation on some subject domain of object. They do not include the identity relation. If X is a positival class, Y and Z fall under the concept, whose extension is X, then also the sum fall under this concept, while X plus sum of Y plus the inverse of X and the inverse of Y plus the inverse of Z fall under the concept, whose extension is domain of X. The fact that this has to exist to fall under the concept if Y and Z fall under the concept is fundamental to prove abelianity. This is a long discussion about that, whether this is really used or not, but it's necessary for the group of abelians. In the language, my languages were written as following. This is the formula as an abbreviation of this long formula. And you say that X to satisfy this formula is to be the extension of the concept. I quiz X the concept with X as the extension, and then all the conditions are written there. As the identity relation results from composition of any binary functional relation by itself, requiring that O, that is the extension of identity relation, does not fall under a concept whose extension is positive class, and that if Y and Z fall under it, then also the sum does, entirely requiring that if the extension of a permutation falls under this concept, then the extension of the inverse permutation does not. In other terms, if I suppose that 0 does not belong, and I suppose that if X plus Y belong, if X and Y belong, of course, I cannot have X and X inverse belong, because X as X inverse equals 0, and 0 does not belong. Okay? So this is a condition to say that I consider only the positive. Okay?
You say you consider only the
positive part. Because if there is 3, there is only no 3.
So, but then, sorry, let me see if I understood correctly. So you consider this condition that tells you that 0 is not, and it is closed under addition. And then under these two conditions, then you can prove that no element and the inverse belong.
Exactly.
Okay.
This should help to understand that the positival class is the extension of a concept under which fall extensions of permutation that form an additive sibling group, whose addition is this addition, and the domain of such a class is the corresponding group whose identity is 0, such that the inverse of any X is the inverse by the fact of the binary relations. A domain of magnitude is the domain of a positive class. And a positive class is a positive class that is both dense and density complete. So I have the structure of a group, and now I ask that this group is dense and density complete. And this is a positive class, and what is a domain, a positive class, and what is the domain of magnitude is the group associated to this positive class. That is the group associated with demigroup, positive demigroup that is complete and dense. And my proof is also Archimedean and Abelian. I do not need to add that in because I can prove that it is both Abelian and Archimedean. But to prove that the Archimedean, strangely enough, is much simpler than to prove that it's Abelian. The proof that it's Abelian is a mass. Frege spent half of his book to prove that it's Abelian. To characterize the domain of magnitude, we have then to find the appropriate open formula to express the two conditions of density and density incompleteness. It is a little bit technical, so trust me, this can be done. This is the density, and this is the completeness. Okay, if you want to enter the detail, I can show you. It can be done. Here is the more difficult part because Frege. I have to very little modify what Frege does, but it can be done. It's only technical. So now I know what is a positive class. A positive class is a positival class that is dense, is complete. Okay, or better, is formed by the object that satisfies it. Okay. It is now immediately identified domain of magnitude as the object that satisfies this form, the fourth open formula, that is the domain of a positive class. Namely, as the extension, namely as the domains of a positive class. The details may appear hard to follow, but the basic idea is simple. A domain of magnitude is defined as an object that satisfies the open formula, an open formula in a single open variable, namely this formula there. So all my point is to write this formula. In order to satisfy this formula, such an object is to be the extension of a first-level concept, and this concept is to be such that the objects falling under it are extensions of permutation that meet some appropriate structural conditions. This condition makes this last object form when taken all together and thence a complete additive group, whose addition is the composition of the extension of binary relation, and what inverse are given by the operation inverse, also defined on this extension, which make the identity of this group given by the extinction 0 of the identity relation. All that is to be defined by comprehension to become able to write this formula are this composition, this operation, and identity relation, which can be easily done by predicative comprehension. So I need only predicative comprehension. Hence, only predicative comprehension is required to complete the definition of domain of magnitude, which makes this definition take place in a predicative second-order setting, which is probably equiconsistent with ZFC and second-order. Once domain of magnitude are defined, real numbers are to be defined in internal ratio on them. To this purpose, we do not have any path traced by Frege to follow step by step, but only broad indication by him. This is that real number are relation on domain of magnitude. Ratios on domain of magnitude. A natural option, also suggested by many, already suggested by many, for example, by Gammet, is to define these ratios through an abstraction principle mimicking Euclid's definition of proportionality. This presents two further problems. Euclid's definition has recurs to natural numbers to define equimultiple of different numbers. Whereas here does not include the definition of this number, because in order to define this number, I would need impredicative comprehension. Euclid's definition only applies to intrinsically positive magnitudes and can then only define positive ratio. Whereas domain of magnitude includes both positive and non-positive elements, and it is natural to look at a single definition delivering at once positive and non-positive real number. One of the obsessions of Frege is that he does not want what he called what is in English? the piecemeal definition. So I cannot define first the real number, the positive number, real number, then the negative real number, they put them together. I have to define all in only way. Why this? It's a philosophical question that I want to discuss. My point is not that Frege was right. My Frege is that the point is we can do what Frege wanted in this consistent setting. Supposing that A, B, A prime, and B prime are four intrinsically positive magnitude, homogeneous 2 by 2, the Euclid definition could be stated as follows. The ratio AB is the same object as the ratio of B prime, if and only if equimultiple of A and B are always one smaller than the other, one greater than the other, of identical one to the other. Okay? Well, and vary on positive natural number. This is Euclid. If the relevant magnitude form an Archimedean domain, the first or third conjoint in the right side of this definition probably entails this other. So in fact, I only need the first line there, because I proved the domain of magnitude. Hence, all that is required to solve the two problems is rephrasing this condition here without appealing to natural number and to adopt it to the case of magnitude that can be either positive or non positive. Both problems are solvable with the help of appropriate tricks. The first one is openly a Frege one. It's long and complicated. I explain the idea. The idea is the following. I can define a class of relation. Imagine that we work on real number. To precise, but we inspire the so imagine that we work in an additive group. Completely. So for any element of the group, I define a certain relation Fa. And I say that x and y are in this relation is y is equal x plus a. So this relation is the addition of a. Okay. Now, what is a plus a? A plus a would be given by, of course, a and a y. Okay? This means that y is the double of a. But now that I have this relation here, I can take the ancestor. That is, what is the ancestor of a relation? When you have a binary relation, the ancestor is exactly what happened in family. What is my ancestor? I am the son of the son of the son of the son of the son. That is, I have a list, which any stage is composed by two elements and are linked by this relation. Okay? So what does it mean to be a multiple of a certain A? Is to be in the ancestor of this relation with A. Okay? Now, what does it mean? What I mean here, what I need here, is to have equimultiples. But I do not require to know exactly which equimultiples. So I can simply have a condition that says that two multiples are the same multiple. The multiple of A is the same multiple of the multiple of A prime. And how can I do? I will define a formula, and you write a formula saying that A is a multiple, that Y is a multiple of A, and is smaller than a certain other multiple. Okay? So that better, I define a formula that says that both A and B are multiple of Y, or X, and that A is smaller than B. Okay? And now what I do? I write exactly the projection between the object that's smaller of a certain object. And so if I enough as much multiple of A that are smaller than B as multiple of A prime that are smaller than B prime, what does it mean that B and B prime are equimultiple of the original? So I do not need natural number. This is the idea. It's clear? For the question of the positive, it's simply a question to jump a little bit, but the idea is not really ready. What is the idea? The idea is the following: that I take a ratio to be x and y to be something where here this is always positive. Suppose the denominator is only positive, and then I take its sign to depend of x. And if x is positive, the rate is positive. If x is 0, the rate is 0. If it's negative, the rate is negative. So I take x to belong to the positive class, and x to belong to the domain of magnitude associated to the positive class. And so in this case, I write two times, Euclid definition. Problem solved. Okay, so the two problems can be solved anyway. And now, finally, I can define what is a real number. What is a real number? A real number is an object x such that exists a y that has certain property p and a z that fall y that fall under a positive class, z that fall under the domain of the positive class, and a y that is a positive class. Z that fall on the domain of positive class, that is can be positive or negative, and y that fall under the positive class, that is only positive, and x in the ratio of z and y. Now you can say, okay, but now you use the in predicative relation, in predicative comprehension, because to define R, you are quantifying with the formula. No, no, my dear, because what I write here, when I write for any p y, what this in abbreviation is for any y, if a certain formula in y, then blah, 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 blah. And this formula does not mean to be a predicate. So here I can mean all the quantification they want. So of course in the formula for p, domain of y, and domain of y, there is a second order predication. But I have no predicate, I formula. So this is predicative comprehension, not in predicative comprehension. Okay? Now I have my real number that makes real number object, x a real number, it will live with the ratio on whatever domain of magnitudes. Notice that Euclid allows the ratio to the element of a certain domain of magnitude to be identical to the ratio of two elements of another domain of magnitude. And this definition, you have the single domain of real numbers, not one domain of this number for any domain of magnitude. This seems to be the definition that Frege was actually envisaging, but never achieved, but restated within a consistent predicative setting. To conclude my talk, let's now shortly take a question and answer it. How is it possible that a so weak setting as the adic second order logic plus BL5 and predicative comprehension is not appropriate to define natural numbers, but it is rather so to define domains of magnitudes and only requires the addition of Euclid to explicitly define real numbers? One might protest by arguing that this setting is actually appropriate for defining real numbers, and what is not appropriate for is rather proving that any natural number has a successor. And adding that I have in fact avoided here to show that this setting is actually appropriate to prove the basic theorem about real number, namely that they form an appropriate set. I reject this objection on the two following bases. Putative natural numbers that are not probably infinite, many, are not natural numbers, in fact. So I not can prove the existence of the successor, I cannot say that I define it. Certain, I did not give the proof that real number, defined as I said, form an appropriate field, but I do not see any principal difficulty without using a predictive comprehension. This is routine. I come then to the answer I shortly suggest. The crucial difference between the definition of natural numbers and that of domain of magnitude that makes the former require a stronger setting than the latter is this. In the former definition, natural number, it is crucially relevant to be able to provide individual specification for 0 and 2 successor. Is any natural number should be individually identified. And to prove that for any of them as a successor, we also need to explicitly define the successor in terms of the predecessor. When I prove for any x exists a y such that y is the successor of x, I have to construct y starting from x. So I have to identify specifically the y that is in question. In the latter definition of real number, we only need to provide an explicit definition of the extension of identity relation without saying nothing specific about any other magnitude whatsoever. Of course, much more than this is required to define real number and to work with them. Still, this is something that only Euclid allows to do. Insofar as it allows to define the real one as the ratio of A with A for whatever positive class P and whatever A in it. More than that, using addition and composition, we can then even identify the real positive and negative integer and the real rational, and come back to the arithmetic of natural number. It is, if possible, however, it's only because of great strength of Euclid, not at all because of predicative comprehension. Answer to following. One point to anticipate Daniele's question. In this setting, I, of course, cannot prove the real number exists. To prove the real number exists, I need something more stronger. But also, this is also what Frege imagined. Leave the definition, prove that it exists, I go outside the theory. Outside the theory, prove that it exists. In the theory, it's logic, I cannot prove that infinitely many, continuous many objects exist. So Daniele, do not ask me how can I prove. I can prove if I construct a model outside the theory, obviously.
This goes back to an old fight that we had.
So then you can argue that this definition is not satisfactory because of that. No problem. It's not my point, it's satisfactory. My point is Frege definition is consistent. This is also what I want to say. The crucial difference between the case of natural number and that of magnitude is not one of cardinality, but one of individual specification. So why I can use a weaker setting to define real number? Because I do not need to specify real number. The only one to specify is 0. When I define natural number, I have to specify one by one. And so the request of specification is what requires in predicative comprehension, not the request of cardinality.
But you can specify one, no?
You can specify if you have Euclid. But when you have Euclid, of course, the setting is stronger because you add a new action, of course. But without Euclid, that is in the setting that you use for natural number, you cannot do it.
But in your definition of the real numbers,
And
you eventually you have to prove that this is a field.
no, that exists a field. No, what's the question?
You have to prove. You said that you are defining the real numbers, right? So for the definition to be a correct one, it should be so that you can prove that it is a field.
That it exists.
That it exists.
It is a field. I think that I can do.
And then it has a one. It has an identity.
But,
No?
Of course.
Am I
Of course.
lost?
of course, what is the identity? The one. If I prove that it exists on the domain of magnitude, not in the theory, I cannot prove it in the theory. If I prove outside in the theory.
Yes.
So I suppose that there is at least the existence of the domain of magnitude is obvious because the empty set is a domain of magnitude. So what I have to suppose that exists a non-empty domain of magnitude. If there exists a non-empty domain of magnitude, so there is an object on it. Take it A. And now I take the ratio on a certain domain of magnitude, the one that exists, of A with itself. And it is exactly one. But to do that, I need Euclid. So I need a setting that, of course, is stronger than the one that I use for a natural number, because I have an axiom more. So, of course, I can do that, but with a new axiom.
But then I guess the point is, how can you prove you have a field without using that axiom?
Sorry? Oh, without that I can prove that is a field. Of course.
You can, okay.
So you can.
I can prove that is that is a group, but not that is a field. Surely.
Wow.
So all what I say is that I can consistently define domain of magnitude, in domain of magnitude, not real number, in the consistent setting that is done, given by Basel 5 plus predicative comprehension, in which I cannot define natural numbers.
So you can define the additive structure of the net.
Exactly, the additive structure of natural numbers.
Okay.
Then I add another axiom, and I have the real.
Yes, okay.
Yeah.
Okay? What makes individual specification possible in the case of real number is not in predicative comprehension, but the great strength of genuine mathematical tool are Euclid, is the point. So that the path that allows to come back to natural number from the real ones and to prove that it is a field seem to be mathematical rather than logical path. So this does not vindicate Frege logicism. It vindicates its definition, but not its logicism. Because to realize the definition, I need Euclid, and Euclid is definitely mathematics. Thank you very much for your also a appendix in which I prove how to come back to the real natural number, but I don't think that this is the trick. Okay. Question, remark, objection, protestation? Patrick.
I think maybe I know the philosophical objection, but instead of doing all those tricks with the Euclid, why couldn't you just add Hume's principle as an axiom to your predicative theory and then like enrich your language with new predicates? Then you have access to the structure of the natural numbers.
Mhm.
That seems mathematically possible. And then you could define the real numbers. But would Frege not like that? Is there some reason for not doing this, or?
Of course we can do that. This is
That
exactly
seems
what
clean.
this is exactly what Shapiro does.
Is that what you're? Okay.
When I say there are different possibilities, this is what Shapiro does.
Okay.
I take Hume principle and I add the different abstraction principle to define the relative, the rational, and the reals.
Okay.
So I can take the real that to be an extension of the natural. But this is what Frege does not
But
want.
do we need even additional abstraction principles then?
This is something that I was not thinking about. I think that I need something.
You would
If
need,
at least if I want to define a relative and rational and real as objects.
yeah.
If I want to, for example, take reverse mathematics. In reverse mathematics, you have subsystem of zeta 2 in which you define the real numbers, but you are in second order logic, and so you cannot define the set of real numbers.
Yeah.
And so what you do is really not to define real number as particular object, but you define real number as object satisfies certain formula. Okay, so if you want to do that, possibly you can do only with Hume principle.
But is Frege not going to like that?
But Frege does not want that.
Because
Because for him, a real number are objects essentially different in nature than natural one. So the only thing that what he does not want at all is to have real number by extension of natural number. This would be for him absurd.
And
But reason a little bit.
What is
Also,
what is the
sorry,
argument for that? Yeah.
sorry.
Does he have an argument for that? What is the reasoning there?
The basic idea about that is the idea that, so let's say it this way. The usual description of Frege is that he's a logicist. That his main aim is to reduce as much mathematics possible, that is all mathematics except geometry, that is was the idea, to logic. Okay? Not geometry, but geometry according to him required in spatial usage. But now suppose that you are Frege. You are this Frege. This Frege that is not born in Germany in the 19th century, but is born in Oxford in the 50s. You have this Frege. It's called Michael Frege. Okay? It is called Michael Frege. So you are Michael Frege. For the people that does not, Michael is the name of that. You are Michael Frege, and you have defined the natural number in a way that you consider to be logical. And now you want to define real number, and you are logicist. So what you want essentially is real analysis reduced to logic. So what the obvious thing to do? To take real number to the extension of natural number that are logical objects. And what is the most simple way to do? By the Dedekind cut. Only require the order relation, the rational number, but the rational number is in fact natural numbers, ordered in another way. So if you are logicist and your problem is to define a real number of logical objects, and we have natural number, why to construct all this mess? The point of Frege, in my interpretation, is not to reduce the real analysis to logic. The point of Frege is to define real number or what really they are. That is ratio of magnitudes. Because in this way, you can explain the application of that real number to the base of magnitude directly by the nature of the object, what you call the application constraint. So now you have an explanation of what the most important thing are words of Frege. The most important thing are the application. But if you define real number dedicating, you lost what is the most important. Because then you can prove that you can apply. But the proof of the application is given by outside. Is not built into the definition itself. I want a definition that directly explains the application. Because I want the real number to be defined as what it really is. It is a domain of magnitude. So Frege, in my interpretation, is not a logicist. It's someone that wants to grasp the real nature of the object, mathematical object, of its question. And it came back in a certain sense to Greek mathematics by saying to Descartes, my dear Descartes, you have tried to put together number and magnitudes, but number and magnitude are essentially two different things. And what they need is a theory that articulates this relation, not a confusion. So I need a theory of natural number here, and a theory of magnitude here. And where the real number are here, not here. So what he has in mind is a reconstruction of mathematics as a building in a certain way. So it's as a foundational program. But this foundational program is not metaphysics, it's mathematical. It's concerned a certain structure of the mathematical knowledge. Mathematical knowledge is to be reconstructed in this way. Is good, is bad, not my problem. The problem is not to reduce mathematics to logic. The problem is to give to mathematics the right structure. So that to this idea to give the mathematics the right structure, he arrived to give a definition to completely crazy. He defined the number 3 times, but why? Because this is what allows him to give the real nature of what the real number are. So Frege was not a logicist, that is my conclusion.
So I think I am missing something because after this brief discussion that we had, what I was ended up saying is that what Frege did was, or what you are doing actually, sorry, what you are doing is defining the additive structure of the real numbers. But
yes.
But there are those ratios, and the justification to take ratios is to be able to multiply. So there is not only the additive structure of the real numbers, there is also a multiplication somewhere.
Of course.
So it is the one free fragment of the real numbers.
No, because based on definition of ratio, I can define multiplication very easily.
Yeah, but then
this is what I do.
Yeah,
in the appendix.
What you end up defining is the one free fragment of the real numbers.
No.
The structure of the real numbers.
No, I define the field.
Huh?
I define the field of real numbers.
But you cannot define the one.
Yes. Under the supposition that exists at least one non-empty class. If there is one non-empty class, I take any element of the empty class A, and the ratio A is 1.
Okay, then I'm
the ratio of A and A is my 1.
Yes, that's what I.
And now I have the 0, I have the addition, and so I have 0 plus 1. And then I equal 1. And then I have 1 plus 1 equal 2. And I have 2 plus 1 equal 3. So I have only natural number. And then I can also find the rational, of course. So I can reconstruct anything. I can find inside the field of real numbers, I can find the field of rationals and the field of relatives and the relatives. But of course, I need two things. A Euclid, of course, for an axiom, and the supposition that there is at least a non-empty domain of magnitude. If I have not this position, of course, I not take any A because this A could not exist.
But I guess that we go back to the question before. So without Euclid, you really can define the real numbers. You define something that we don't know if it's a real number.
You define the structure of the real number.
Yeah.
Bruno had a question from the Zoom. Bruno, are you there? Can you put the question? Bruno? Hello?
Can you hear me?
Yes.
Hi, Marco. First of all, thanks for the talk. Very interesting. So I have a question regarding your explicit definition of the reals. So I was wondering if Frege wouldn't object that a certain Julius Caesar problem would arise with respect to ratios, because you defined the predicate RAT by terms of invoking a contextual definition, right? So I'm concerned that Frege would object that there's a certain kind of referential indeterminacy concerning the
So you
reals.
mean a Caesar problem for ratios?
Marco, can you please mute your...
When I speak, there is a master. So if I speak, you cannot.
No, both of you can speak.
No, speaks. Bruno speaks. Try to speak.
Yes, right. Okay, I muted myself, but I'm not sure if you could hear me just now.
Yes,
Yes, we can.
Yes, right. So that was mainly, so should I repeat the question or?
No, did you hear the question?
Yeah.
Oh, yeah, yes, that's, yeah.
The following. Frege object to Hume principle. Why Frege does not take Hume principle as action? They want to prove a Hume principle as a consequence of externality. Because he says Hume principle gives identity condition for natural number, but does not explain what the natural number are. So he cannot answer the question whether Caesar is a natural number or not. Example is famous, and so it is called the Caesar problem. The Caesar problem is simply that we have a condition of identity, but not condition of application. We can think what you want of this argument. What is clear is basic law 5 also is a contextual principle. So also basic law 5 does not give you a characterization of what extension are. It gives only a identity condition for extensions. So how Frege could reject, Frege does not never discuss that, but it seems to suppose that extension in some sense is given directly with the concept. If the concept is given, immediately is given after the extension. And so in fact, the basic law 5 does not introduce extension because extension already there together with the concept, it simply gives it the identity condition. On the contrary, numbers are not directly there with the object, with the concept. So I need something more. So if I use Hume principle, I need to know what numbers are, because numbers are not directly given together with the concept of which they are numbers. Okay, you see, follow? So the question of Bruno, you agree about this reconstruction? The question of Bruno is the following. Also for the Euclid, I say ratio of A and B is identical to ratio of BC if indeed it is. I give an identity condition, but I don't say what is a real number, a ratio. So I found a sort of analogous of the Caesar problem for the ratio. Okay, this is the question. Now, we do not have Frege definition of real number. So we do not know how he would have done. Up to now, neither me nor Dummett nor others have never imagined a non-contextual definition of real numbers or ratios. So Frege had in his mind a non-contextual definition? We don't know. If he had in his mind, we are not intelligent enough to find it. If he did not have it in mind, he should have given an argument in favor of taking the definition of ratio not submitted to the Caesar problem. Which this argument would have been, I do not know. Very probably that to be a ratio is not to be an object of a particular nature, but to behave in a certain way with respect to magnitudes. And so, in some sense, magnitudes are there. Logic does not give you magnitude. Empirical science or geometry gives you magnitude. The only thing the logic does is to explain what is a magnitude, what is a domain of magnitude, to recognize length per magnitude, weight per magnitude. Okay? So the magnitudes are there by empirical science. Now, what logic does is simply to tell you as the ratio of the things that are there behave. And this is all what is required. Is a good response to the Caesar problem for Euclid? I do not know. What is sure is that Frege wanted to define a real number and ratios magnitudes. There is no other apparent way up to the moment. There is no other way. Frege does not give any suggestion about how to do it because he did not write the volume. Nobody has invented a way to do it that is not by abstraction principle. So take the conclusion that you want. My idea is that insofar as Frege had already an exception to the Caesar problem, this particular file, he could have accepted also Euclid as an exception of Caesar problem for some reason that I cannot imagine. Okay, other questions? There's no other question. Daniele, you have no objections?
No, I voiced my objection before.
The permutation.
I have an
No,
objection.
but this I wanted to try to clarify the point.
More than an objection, I should say, I have no idea what you mean when you say that. Let's clarify.
What I say that is what you
It's deeper than an objection. So go back to that definition if you want, that commentary, and explain what you mean by that.
permutation.
Yeah.
So I have a relation. Okay. What my object at the work are not the
Go
relation.
back to the slide that you used when you talked about this, so we put that in context. La diapositiva di dove eravamo.
Where?
Was it the very earlier than that? I think he was still in the introduction.
Introduction.
Okay, no, it's.
Yes. No. Okay.
Okay, here we go.
So what's the point?
So the definition is structure as required under a concept with a distinctive domain of magnitude only for extension of binary relation working as permutation on a subject with. I don't understand how this connects the domain of magnitude, which now in my mind are, after you told me, are
The group?
a group, but they're also these magnitudes are really pairs of. I think about as geometrical objects. Am I allowed?
Yes.
Okay, I never know what I'm
They are.
in this context.
No.
So what is permutating? That's what to understand. What is permutating here?
No, that's all. The first idea, segment are not magnitudes.
Right,
Lengths are magnitudes.
right.
Okay. So, what is the length of this segment?
Well,
It depends on what I choose.
Right, you have to choose a unit.
So now I have my structure, and what is relevant is not what is the length. What is relevant is this length, the half, with relation to other length.
Right, so the relation.
Other length. So now I have
You take a
one
pair. You take L
electron,
in
this with respect to a certain unit.
exactly.
Now I have L prime 1, L prime 2 with respect to another unit.
Correct.
What is relevant is not what it is R. What is relevant is the structure that it is satisfied, that should be the same that the structure is satisfied, that it is smaller, is 1, for example, etc., etc., etc. So now, if I understand well, the permutation in question are the relation that connect this segment to this segment, that make it length. it lacks, it's not a natural number, it's a ratio between that and that.
Right.
And the ratio can be another ratio if I permute, because I change the unit of measure. But the structure is the same.
Maybe then you don't mean by permutation what I meant by what I thought.
Yeah, it's more like.
Yeah, yeah.
Or,
Yeah, maybe that's just a
Orient.
linguistic problem.
I think so.
So a
Because
permutation,
permutation is when you have a finite set and you have all the possible permutation of the elements in that set.
But permutations are, in the sense, the relation R, the relation between the segment and the other segment, that have these properties that are functional and bijective on a domain.
from the domain into the itself.
The domain that it is, for Frege, is the totality of objects. That's another crazy idea. Let's say a set of subjects and objects. So now you want not to think them a permutation. Mathematically speaking, they are permutation.
No, this is a permutation, but what we do not understand is how these are permutations, how these things that you're explaining are permutations. What is,
Because in definition, it required that they
by-
are
by-
R be functional.
what is sending, what is the input, what is the output? You said that permutation is a function, or is functional.
Yes.
Or however you want
Yes,
to put
this
it.
binary relation, it's a functional binary relation. And it's a bijection.
So the function relation here is between pairs of these magnitudes. But then I still am confused that.
Because there's a lot more structure than just being a bijection.
You see.
Is there an order? Or?
Look here. This is the definition for the vectors. In this strange formula, this here means the y. That is the y is the extension of a relation. Okay?
Okay.
Y is functional. This means y is functional. Okay? This means that it's inversion
Why?
functional. And this means that the domain is closed under it. That is a permutation. So what I mean by permutation is my relation R satisfies this condition and these conditions. That's it.
So if I take just some permutation of the natural numbers, whatever you want, how do I define addition now?
No, because I want to be permutation of binary relations. This is fundamental. So I want extension of binary relation. So the addition is the composition of the binary relation. So what is x plus y is z. What does it mean then? It means that both x and y are extension of a relation. Y is extension of S. And Z is the extension of the relation
Of the composition.
R composed with S.
Okay.
This is, the natural number I cannot do it because natural number are not extension of the relation.
Sure, but there's no guarantee of commutativity.
No, absolutely not. And for this, I need that. Is required.
So he builds, so it's more than just a permutation. These are.
It's a commutative, yes.
These are very specific permutations.
Yes,
are-
of course.
that are
It's a
committed to the
permutation that
version.
satisfies these other conditions.
Whose iterates are.
And
committed
this,
under permutation-
this
under
condition
computation.
here is a very complicated condition because Frege tried to use it as less as possible. It tried to prove all what it can without using this one. And in fact, it proved Archimedicity without using this one.
So what you're saying
And this
is
condition
relation have to
is
be
only
invariant.
used in order to prove
Yeah,
commutativity.
right.
This relation have to be invariant under permutation.
Exactly, if you want. It's invariant under permutation. If you want. And
But then this doesn't seem to be, I mean, it seems like you're not really taking.
but now I want to show you one thing.
Yeah,
I want to show
Exactly.
you one thing.
No.
No, is the extension of a relation that works as a permutation, as I said.
but not any such thing. It has to also have this extra property.
Right.
It has the mathematical property of a permutation.
Yeah.
Let's say it this way. I want to show you a citation of it. That is the citation by Gauss that is used in order to justify this idea. And according to his interpretation, Gauss is telling us that magnitude are, in this sense, permutation. So let me find that is citation.
So if you have a quote from Gauss, we'll be happier.
Sorry? Sorry?
If you have a quote from Gauss, we will be happier.
Yes, I have the quote of Gauss.
Okay, good.
But I have the quote of Gauss quoted by Frege. Then I also the general Gauss, but it's more difficult to find. Here. Classic closure arithmetic. No, this. Yes, this one. Where it is, I have to go somewhere, so it's long. Let's say that it should be this. Where we are here. It's much before. Here. Is presenting his definition. He say, since our initial concern is to obtain a foundation just for the theory of the real number, we will simplify the matter by leaving absolute magnitude out of the consideration. Temperature is not a good magnitude. Focusing only on those domain of magnitude in which there is an opposition corresponding to that between the positive and the negative for the measuring number. Here a remark by Gauss may be proved F. Here is Gauss. Positive and negative number can find application only where that which is counted as an opposite, so that thinking them in union amounts to annihilation. Properly speaking, this presupposition is that only when was discounted a relation between a relation with R is Frege use two words for relation, one to mean relation, that is the German word, this relation in German.
Relation.
Sorry?
Relation.
Yes. And then
Or Verhältnis.
and the other is a relation, it is extension of relation. It's supposed to use relation with majuscule is extension of relation. Between any two objects and not substances, it is thereby postulated that these objects are ordered in a specific way in a series A, B, C, and that the relation A to B can be regarded as equal to the relation B to C, etc. Now, nothing more here pertains to the concept of opposing than the exchange of the member of the relation in such a way that if the relation or the transmission from A to B count as +1, then the relation from B to A will be represented by -1. Thus, insofar as the series is unlimited on both sides, each real number represents a relation between a member which is arbitrarily chosen as a beginning and a specific member of the series. So, Frege command, in a sense, we can agree with this talk, omitting, however, the restriction to all number and replacing what is counted to what is measured. It seems that Gauss thinks a relation as determined by the object among which it holds and require a postulate about the quantity of relation, etc. We overall regard the relation as definable without append to specific object, etc., etc., etc. And then when we define a relation, is thus the condition that satisfies this condition of being injective, of being functional, the inverse functional, that is injective.
So he never really talks about it.
No. The word
Exchange.
permutation is not in
He
Frege.
uses, I'm sorry, he uses the word exchange,
Exchange.
Gauss, right?
The word the permutation is introduced by Dummett. It's not in Frege. But mathematically, they are permutation. Frege does not. You don't want to call permutation? There are bijective relation on a closed domain. You like better than
No, I don't like that.
This is what they are.
I remain the skeptic in this room, forgive me.
You're not alone.
But in any case, again, my point is not to defend Frege.
Right.
My point is that I can make Frege consistent.
Really?
Sorry?
I think,
No, it's not to defend Frege.
no, we don't need to defend, we love Frege.
No,
But
I just finished a book in which I give a definition of real number completely different than this one. No. This definition is very nice for me.
I'd like to, not now, but maybe you can show me the piece of this other guy that introduces this idea of permutation.
Yes.
I want to understand how that is done, but
Okay.
I don't want to.
Okay, but
Everybody
in any case, so when I said that permutation, it means simply, as Dammit means, that they are
Projective
binary relations that are both functional and the inverse is functional and are closed under on a domain that is closed under them. Okay, so they are rejection of this domain, essentially. Okay, then is a good definition? For many sciences are very good because it essentially give a reason of the applicability in the definition itself. For other is absolutely non-economical. We have a lot of things that are structurally irrelevant here. We define real number 3 times, for example, to say only one. So if we want to be conceptually parsimonious, this is horrible. There is no doubt at the moment. But my point is that Frege was wrong in giving up the definition because of inconsistency.
So what I think is, so what would be one of these particular relations?
Yes.
So imagine that we already have the real numbers because I want to take it as an example. So one of these relations will be the one that relates the unit interval with the interval 0, 2. And
Now, one of these relations will be, so you can construct different models. This is one of the models. One of these relations is add B. So what is for X and Y to be in this relation is to be simply in this. So this relation here is B. So there are as relation as real numbers.
okay.
And this is the relation in question. In a certain model. Now, this relation we have as a permutation. Call it in another way if you want, but we have as a
I
permutation.
see.
So this is the relation in question.
Okay.
In a model, and you can construct another model. But in the intended model,
So you're
this is the
picking a
relation.
class of permutations that are invariant under each other.
So what are the permutation here? What are the permutation? It take X in Y.
Yes.
So it take, this is B, it take the X here.
In my mind, I went
This is
to
the
be
permutation.
multiplicative, and then I was thinking that the relation that existed in the segments is that those segments are in
No,
proportion.
the relation is the one that take it here and they put here.
Suggests that,
Yeah.
but
But it
that's
is
not
not.
what's going on.
Yeah.
And it is mimic the change of a unit of measurement.
Yeah. No, yeah.
So that's nothing, it's very simple, it's nothing than that.
You have one relation like that is adding B. You have another relation that is adding C.
Exactly,
And then the composition will be adding B plus C
exactly,
whenever B plus C is
exactly.
one.
It's nothing by that. Of course, this is a model. It does not want to say that this is this one. You want to say, maintain the other relation that is property.
Yeah.
But this is the intended model. And this is a permutation.
Yes.
Because they take X and they put here.
Yes.
The translate of B.
Yeah.
And then I have the permutation translate of B, the permutation translate of C, the permutation translate of D, and the permutation that came on the other direction, is the negative. And then I have the permutation that add nothing, that is the 0.
That's why the inverse is is just the reverse.
Exactly. Why? Because you simply, instead of put here, I put here.
Now let's
It's clear, Daniele?
I still don't think you should call those things permutations. I mean, that's a very misleading term. It's very misleading. That's my view. I mean, the guy who made it, that's fine.
Okay.
Yeah.
Thank you. I will.
For us, it's a very technical term, and it really just doesn't mean that.
Do you, so, Daniele, one thing that I did not know about you.
So,
a permutation is a rearrangement, so it's a bijection of a set within.
So one thing that I did know about you, Daniele, that you are an essentialist. For you, a
I'm just saying.
permutation is not something that
Then you
behaves
think
as a
about it.
permutation. For you, a permutation is not something that behaves as a permutation. Is what is really essentially a permutation. Something that behaves as a permutation is not a permutation, even if behaves as a permutation. So you know essentially, metaphysically, what is a permutation, and to reject anything that behaves as a permutation, that satisfies its nature of really being a permutation. Well, and in fact, to defend myself, my dear friends, because then you attack me and I defend myself.
I didn't attack you, you said
No,
that
you
you have a comment to make.
You defend me, you attack me, you want to fire me by this university. I want to show you one thing that will definitely close the dispute with us. What I say here is not that they are permutations. I say they work as permutations. You remember?
Oh, okay.
They're supposed to put an end to it.
Wow.
It's written here.
It depends on what is.
Yeah.
I show you, and then
It's
the
okay, my
dispute is
friend.
definitely won by me. Relation working at permutations.
We have a question for
Yeah,
Giants.
question.
Sorry. Even that, it's written 5 times. 5 times.
We have another question for Peter.
Peter, go.
Hi. Thank you for a very interesting talk. I think I finally understand what these are.
Okay.
This is, Frege is talking about the Cayley representation of the real numbers in the set of functions from R to R under addition, right? And those are, of course, permutations because that's what Cayley uses. And if you look on the graph, they're just diagonal lines. You know, the 0 is the diagonal line x equals y, and the other ones are parallel to it. And they are definitely permutations, but it's a very special way of thinking about the real numbers. And you have to abstract very much to, you know, to see them logically rather than just algebraically. And I mean, in this representation, we're starting from the real numbers, but Frege is trying to start from logic and build this representation. But that's these linear.
They do not listen. Simply, it's not that they don't understand. They do not listen.
So Cayley's theorem says that every group is
A group of permutations.
a subgroup of a full permutation.
Of course, yes.
And so Peter's pointing out is the one you've just described is the Cayley representation.
Absolutely.
Of the reals on the reals
Absolutely.
of the additive group.
Absolutely.
So in that sense, yes, these are permutations, but I think Daniele's objection and many people is that that's misleading because it's not true that you can take any submonoid of the permutations. That won't be a domain of magnitudes. They have to be closed under. They have to be invariant under each other for that to even work. And that might be enough. Actually, that might be enough.
To be
have them invariant under
permutations,
each other might
to
be
be
enough.
permutations is a necessary condition in definition, not sufficient.
Yeah, that's
That is
I
clear.
think that's
They
the
have
part
to be
that people
permutations that satisfy certain
Yeah,
conditions.
I think that's
Now,
objecting
this
to
is
using that
also
word.
the reason for which I said at the end of the story, it defines magnitudes and an additive group. I do not add additive group of permutation. Why? Because for Cayley theorem, any group is in a sense strong of is a group of permutation.
Yeah.
So simply give the group under the representation of the group of permutation. Why does it? I think for two reasons. One is to be close to Gauss that is interpreting his way, but the other is simply because it's technically very simple.
So can I take this?
Insofar as you
So can I
want to,
take a domain to be any group, any permutation group that is closed, that's commutative?
that is complete, dense, Archimedean, and commutative.
For the reals, but just a domain of magnitudes?
The minor magnitude also commutative. Is Archimedean, complete, dense. With the only difference that completeness and density are given by the definition. Archimedicity and abelianity are proved as theorem. for the abelianity in a certain way, because the abelianity requires this condition that is there is not exactly
Yeah, the one that you
the
showed.
one that is only used to prove abelianity.
Yeah, yeah.
And so it does not tell directly that it's abelian, but together with the other, give the property of abelian.
Okay.
So in sense, abelian is in the definition itself, in a sense. But the Archimedicity follow by the completeness. That's us today. Okay, so I think that we can stop here. Thank you very much.